distinguished guests, ladies and gentlemen, it is indeed an honour and a pleasure to welcome you here to Asian University today to the Nobel Laureate Lectures. In particular, a very warm welcome to our special guest, Professor Cohen-Tannoudji and his wife. Asian University are proud to be part of the Bridges events, sponsored and supported by the International Peace Foundation to promote the Kingdom of Thailand as a centre for dialogue and international understanding. Our Master of Ceremonies today is Mr. Napat, the President of the Student Union and third-year engineering student. In handing over the ceremonies to Mr. Napat, I would just like to once again welcome you very warmly to Asian University. Thank you.
Thank you, Dr. Neil. So, good morning, Professor Cohen-Tannoudji, distinguished guests. Today, we are greatly honored to have us Nobel laureate, Professor Cohen-Tannoudji, to speak to us about his work and his idea. Professor Cohen-Tannoudji was born on April 1st, 1933, in Constantine, Algeria, which was a part of France. I believe that the name Cohen-Tannoudji simply means the Cohen family from Tangents. Professor Cohen-Tannoudji went to Paris in 1953 and was admitted to the École Normale Supérieure. He completed his PhD in 1962 after serving in the army and continued research at the École, the Department of Physics. At the École, Professor Cohen worked on the theory and new mechanism for cooling vacuum atoms with laser light. In 1995, Professor Cohen and his team cooled helium atoms to within 18 millionths of a degree above absolute zero. Atoms at this temperature have a velocity of about 2 centimeters per second. This work improves scientific understanding of how light and matter interact, and the technique developed to cool atoms allow them to move slowly enough to be examined in detail. Professor Cohen-Tannoudji, together with two other researchers, was awarded with Nobel Prize in Physics in 1997. This work has many applications, and we look forward to the speech from Professor Cohen-Tannoudji. And before I call on him to deliver his talk, I would like to ask the President of Asian University, Dr. Nipan Ria, to address us. Thank you.
Professor and Madame Tannoudji, and staff from Asian University, and guests and friends and students. It's a great pleasure to welcome Professor Tannoudji to our young institution here. And as Professor was arriving, I was giving him a short story that I started this university more or less as a retirement hobby, which is very strange because retirement means not to do anything. But retirement starting at university means I have to do much harder work than I have ever done before in my life. And when we started the university about 8-9 years ago, it was our intention that once a year we would like to welcome top leaders in their field to come and give a talk at our university so that all our young students would have a chance to look at some role model for the future. Nowadays, because of the availability of television, radio, entertainment, I guess a lot of students have lost that, what we call role model thing. So the first year we invited a professor from Sussex, Sir Harry Cohen, to come and give a talk on how to find carbon-60. And the second year we invited Dr. Edward de Bono to give us a talk on his lateral thinking. And the third year we invited Professor John Vernon from Imperial College, who managed to salvage the leaning Pisa Tower to bring it back to be stable for the next 800 years. And this year we are so honored to have Professor Tannoudji with us. And I'd like to welcome him. And without further ado, I'd like to introduce him to you. So please welcome Professor Tannoudji.
Thank you, Dr. Whitman. The International Peace Foundation has made the physics by Nobel Prize to Thailand possible. So now, ladies and gentlemen, I have great pleasure inviting Professor Cohen-Tannoudji to deliver his talk.
Dear colleagues, ladies and gentlemen, students, before starting, I would like to say that I'm extremely happy to be here and to visit this very beautiful university, Asian University. And as you said, Mr. President, you did a very nice job after your retirement. It's a fantastic enterprise to build such a nice place and to attract good students, good people to start a new place for doing research and education, higher education. So I wish you the best for the success of this very young university. Thank you very much for inviting me here. Thank you very much also, Mr. Mohamed, for inviting me in this program of the International Peace Foundation, which I found extremely stimulating to bring people here from all cultures in science, arts, humanities, and to give them opportunity to talk to people, to exchange ideas, to dialogue, and finally to promote, as you said, mutual understanding between people who want peace for mankind. So my lecture will deal with the manipulation of atoms with light, and since I was not knowing exactly at what level I should start, I prefer to start slowly with a simple notion and then to try to explain to you the latest development in this field. So what I would like to do is to address a few questions, a few basic questions, such that what is light, and show you that our ideas on light have changed progressively from a wave to a set of particles called photons. Then I would like to discuss how does light interact with matter, with atoms, and I will introduce a few ideas about quantum mechanics and about the elementary process of emission and absorption of photons by atoms. Then I will ask the central question of this presentation: can one use and can one master atom-photon interaction for getting information in the atoms and for manipulating them, for controlling their various degrees of freedom? And I will give two examples: optical pumping and laser cooling. And also, I think it's very important when we give a lecture like that to try to discuss what are the new research fields, the new perspectives opened by this discovery. What can we do with them? So let me start with light and remind you first that for a long time, light has been considered only as a wave, an electromagnetic wave consisting of an oscillating electric and magnetic field, oscillating with the frequency nu and propagating in free space with the velocity the order of 300 kilometers per second. And at a given time, light is represented by a sinusoidal perturbation, like that, with a spatial period, lambda, the so-called wavelength, light wavelength. And as all wave phenomena, light can give rise to interferences, fraction effect, which are well known for in high school textbook. And just let me remind you the well-known Young experiment. If you take a light source and a screen with two slits, A and B, and an observation screen, and if you ask what is the repartition of intensity on the screen, you find the following result. You find that the light starting from S and ending to M can follow two different paths, SEN and SPN, and depending on the position of M, the two waves arriving in M can be in phase, in which case the amplitude doubles, or out of phase, in which case there is destructive interference. So if you study how light varies, we have a series of maxima and minima of light intensity. This is what is called interference fringes. But at the beginning of the last century, it was discovered that light is not only a wave, but it's also a set, an ensemble of particles called photons, and having an energy E and a linear momentum P. And that was the contribution of Greek physicists like Max Planck and Albert Einstein. And the basic relation obeyed by E and P are called the Planck-Einstein relation, and they showed you that the photons associated with the light wave with frequency nu have an energy E and a linear momentum P given by E equals h nu, P equals h nu over c, where nu is the frequency of light, c is the light velocity, and h, the basic constant of physics called the Planck constant, introduced for the first time in physics by Max Planck in 1900. And what is important is that you cannot consider light only as a wave or only as a set of photons. Most descriptions are essential. And light is at the same time a wave and a set of particles. And this is wave-particle duality. Now having introduced light, I can say a few words about atoms, the other partner. You know, the first model of atom was the planetary model. You have an atom consists of electrons, which are light particles with a negative charge, orbiting around the nucleus, which is much more massive, with a positive charge. But if you take this model seriously, then you predict a lot of things. The charged particles, as they're going in accelerated motion, like this one, should radiate energy and lose energy. And progressively, it will fall on the nucleus. So the first prediction is that atoms should be stable. They should collapse. Second prediction, when they go to the nucleus, the frequency of the motion changes, and the frequency of the light which is emitted changes. So we have two predictions. Atoms should be unstable, and the emitted spectrum should be continuous. But of course, this is not what is observed. Atoms are stable, we exist, we do not collapse. And so that when you look at the light emitted by atoms with the spectrometer, you find that the frequencies which are emitted consist of a series of discrete frequencies. You have a discrete series of light. And to understand that, that was the starting point of a new era in physics, the quantum era, the quantum mechanics. And the first step was done by the French physicist Louis de Broglie, who in 1924 introduced the revolutionary idea, the idea that wave-particle duality applies not only to light, but also to matter. And the idea of de Broglie was to say that with every matter particle, with mass m and velocity v, it associated the wave with the wavelength, here the lambda, in the computer, lambda de Broglie, which is called the de Broglie wavelength. It's a called the Brownian wave, given by this formula, lambda de Brownian equals h over mv, h is Planck constant, and the mass of the particle, v the velocity. Then, a few months later, Erwin Schrödinger, extended the idea, and he showed that every particle is described by a wave which is called wave function, obeying a famous equation which is called now the Schrödinger equation, and it describes most of the physics we observe in the microscopic scale. And of course, I have no time here to explain what is Schrödinger equation. Let me just tell you that when you try to solve these equations, you find that only certain solutions of this equation are physically acceptable, have a physical meaning. And these frequencies, for example, have a certain oscillation frequency. That is to say, a certain energy, because in physics, in quantum physics, frequency is associated with energy. That means that if you consider the physical quantity, it is quantized. It can take only discrete values. And in particular, the energy of an atom in the rest frame, the energy of the electron, the various possible oscillation frequencies of the wave function correspond to well-defined energy. And to represent this energy, we draw a line. This is magnitude proportional to the energy. And that is the lowest possible state, lowest energy, which is called the dawn state. This is the first excited state, this is the second excited state, and so on. And we get in this way what is called a spectrum of energy levels. Now we have described light and atoms, we can describe now how do they interact. And they interact by basic elementary processes which are called emission and absorption. In emission process, an atom starting from an upper state, B, can go to a lower state, A, by emitting a photon h nu. The reverse process is called absorption. An atom starting from the lower state, A, can go to the upper state by absorbing the photon h nu. And there exists a very important relation between h nu and the difference of energy between the two states, EB minus EA. And that equation is just the conservation of energy. When the atom goes from B to E, it loses an energy, EB minus EA, and this energy is carried away by the emitted photon. For the atom to go from A to B, it needs to gain some energy, which is given by the absorbed photon. So this is conservation of energy, and the consequence of this equation is that if you measure with a spectrometer nu, the frequency of the light which is emitted, you can determine EB minus EA, and you can reconstruct the energy diagram, spectrum of the atom. And that's what is called the principle of spectroscopy. And the important feature of this is that the two different atoms, hydrogen and sodium, for example, have different spectra. In other words, the spectrum emitted of light is a fingerprint of the atom. By looking at the spectrum, you can identify what is the emitting atom. And it is in this way that we get all information we have on the universe. By looking at the light coming from planets, from stars, from galaxies, from the interstellar space, we can identify what are the atoms, the molecules, which constitute this media. By measuring the Doppler shift due to the velocity of this light, we can also detect that the universe is expanding. So you see here that light is essentially a source of information on the structure of atoms. So I will skip the next few slides to go a little faster. And I would like now to the other idea is that light is not only a source of information on atoms, but it is now considered more and more as a tool for acting on atoms. Because by letting atoms interact with light, we can capture atoms, we can modify their position, we can modify their velocity, we can control them. And how do we do that? We do that because the total energy, the total linear momentum, the total angular momentum is conserved when an atom absorbs a photon. So we can transfer, we can have resonance exchanges of energy, angular momentum, linear momentum between atoms and photons. In other words, we use the basic conservation laws of physics for manipulating atoms. And let me first give you an example of this idea, which was the oldest one, and which was developed by my thesis supervisor, Alfred Castell, who got the Nobel Prize in 1956. Let me discuss how it's possible to polarize atoms by exchanging angular momentum between atoms and photons. First, let me remind you, let me explain to you what is angular momentum. You know, atoms have an angular momentum. In fact, if you think of atoms, you should consider them in a simple way as spinning tops. They rotate around themselves like a top. And they have an internal angular momentum which I call G, capital G. Now, as all physical quantities, the projection Gz of G along the z-axis is quantized. It can take only discrete values. And if I take a simple case of an atom which is what is called a spin 1/2 atom, then Gz can take only two values, spin up or spin down. That's the quantization of angular momentum. Only two values, spin up, spin down. Now, since you have a rotating charge, you have also a magnetic moment. And the magnetic moment can take only two values, plus or minus, with a certain value. So if you put an atom in a magnetic field, these two magnetic possible values of Mz correspond to two different magnetic energies. So you have two spin states. Here it's narrow to the up and narrow to the down, spin up, spin down, separated by a splitting proportional to the magnetic field B, and which can be written as h nu z, where h is Planck constant and nu z frequency. If you apply the radio frequency field, electromagnetic field, with frequency nu z, you will induce absorption and emission concept between these two states. People say that you can flip the spin. The spin is flipped from plus or from minus to plus, and this is what is called magnetic resonance. Magnetic resonance, which is a very important field of physics, it corresponds to radio frequency transition between the two spin states. Now, if you take an ensemble of atoms at room temperature in low magnetic field, usually the two spin states are equally populated. The thermal equilibrium corresponds to nearly equal population of spin up and spin down. You have a little more spin down than spin up, but the two populations are nearly equal. And the magnetic resonance signal is proportional to the difference of the number of spin up and spin down. So the magnetic resonance signal is small if you have a small number of atoms, and you need to have a large number of atoms to get a detectable signal. And this explains why at room temperature and in low magnetic field, magnetic resonance can be only detected on dense systems like solids or liquids, because then you have many spins, many atoms. But it's very difficult to observe magnetic resonance in gases, in dilute substance. But then the idea of Alfred and his colleague there was to use light-atom interaction. Why? It's because whereas it is difficult to polarize atoms, it's much easier to polarize light. You use a polarizer like the polarizer you have in your sunglass. And in physics, the photons, you can show that photons also have an angular momentum, and that this angular momentum depends on the polarization of the wave which is associated to the photon. So if you polarize the light beam, which is easy, you get a set of photons which contain angular momentum. And when atoms absorb these photons, which contain angular momentum, they gain the angular momentum of the photon and they become polarized. And this technique, that I'll give you the general idea, allows you to polarize atomic samples in a gas phase with efficiency of about 90%. Okay, you can have 9 more population of the spin hat 9 times larger than the population of the down state. And then you can easily detect magnetic resonance in dilute gases. And that has been important because in dilute gases, interaction between atoms are less important. The magnetic resonance lines are less perturbed by the interaction, and you can make much more precise measurements. So that brought a lot of results. And I would like just today to show you a very recent application of this idea, which was not expected in the beginning when the optical pumping was discovered in 1950. It was this application which I will describe now is very recently, 10 years old. A few people, including, for example, Will Haber in the States and Ernst Otten in Germany, Michel Leduc in France, had the idea that if you polarize by optical pumping helium-3, even though it's an inner gas, it does not attack the body. It's inert. So if you polarize helium-3, you mix helium-3 with air, and you have a patient breathing this mixture, it fills the lung with the polarized gas. And then you can make an image, magnetic resonance image of the lung, of the cavity of the lung. MRI, magnetic resonance imaging. Usually, MRI detects the proton. So the spin of the proton of the hydrogen atoms containing the hydrogen in the water molecule. And the water molecules are in the bone, the blood, the flesh. So MRI with protons only detect the solid of the liquid part of the body. You cannot detect the cavity of the lung. If you have a patient breathing polarized helium-3, you can also detect the cavity. And the next slide shows you 2 MRI pictures. On the left, the usual proton picture, where you see the coast, the stomach, the esophagus, the earth, but you don't see the lung. On the right, you see an MRI picture done with helium-3, and then you see the lung and the cavity. And that becomes now a very important diagnosis of lung disease like asthma, emphysema, cancer lung, bad effect of tobacco, and so on. You see, it's used more and more in the hospital for diagnosis. You see that I like this example because it shows you that important applications, in general, are not planned in advance. They are not the result of programs or governmental programs giving priority. They come generally because some progress in basic research suggests you to find a new application. And that was the case for the laser light, for the invention of the laser light, for the invention of the transistor. Most important applications which conditions our life today come from basic research. Let me also give you another example. Everybody knows now the web, www. But the web was found by physicists, working at CERN. They were getting so many data from their experiments, they were to transmit this data to colleagues working all over the world, and they invited this way of transmitting data by having a separate computer. And that's how the www, the World Wide Web, appeared. So you see most applications come from education. So let me now try another idea, light shift. I introduced this idea because it was useful for the following part of my talk, and in fact that was the subject of my thesis work in 1961. And here, in this case, the idea is that if you excite atoms with non-resonance, exactly non-resonance, if you detune light from resonance, you predict and you observe that the ground state is shifted by light. As it is represented here. For example, if you excite an atom with light with the frequency omega L slightly larger than the atomic frequency omega A, the ground state is shifted by an amount delta Eg, which is proportional to the light intensity. If you double the light intensity, you double the shift. And the shift is positive. If the light is detuned below the atomic frequency, if it is detuned to the red, the shift is negative. So by choosing the intensity of the light, and by choosing the detuning, you can control the energy of the ground state, both in magnitude and in size. And you will see an important application of this later on. So let me now give a second example of resonance exchanges between atoms and photons. Now, instead of considering angular momentum or energy, I will consider now linear momentum. And let me first remind you, I'm sure you have all seen the tennis racket hit by the tennis ball, the racket recoils. It's because the momentum of the ball is transmitted to the racket. You have seen also a gun firing a bullet. When the bullet stops, the gun recoils. The momentum of the bullet is given to the gun. Also, the jet, the plane jet is working by exchange of momentum between the plane and the fuel which is going out. And the same phenomena appear in emission in absorption. And they are called recoil. Recoil of an atom absorbing a photon. Suppose that you have an atom in the lower state G, and you send on this atom a resonant photon with a linear momentum h2 over c. You remember that Einstein showed that photons have a linear momentum h2 over c. The Planck-Einstein relation. When the atom is initially at rest, when the atom absorbs the photon, it recoils. Because the total momentum will be conserved. The atoms jump to the initial state. So the total linear momentum of the initial state is equal to h2 over c because the atom is at rest. The linear momentum comes only from the photon. When the photon has been absorbed, the photon has disappeared, and the linear momentum must be carried by the atom. So the atom must move with the velocity v recoil such that mv, the linear momentum of the atom, is equal to h2 over c. So the atom recoils with the velocity v recoil given by h over mc. Once the atom is in the upper state, it remains there forever. After a certain time, the atom will fall down to the ground state by the process which is called spontaneous emission of a photon. And the time spent by the atom in the excited state is called the radiative lifetime of the upper state. Typically, it can vary from one state to the other, from one atom to the other, but it's typically 10 to the minus 8 seconds, 10 nanoseconds. So after about 10 nanoseconds, the atom falls back down to the ground state by emitting spontaneously a photon in all possible directions, with equal probability in two opposite directions. If it emits the atom, the photon in this direction, it's recorded in this direction. If it emits the photon in this direction, it's recorded in this direction. So on the average, because of the isotropy of spontaneous emission, the momentum lost in the emission process is equal to zero. So contrary to what happens in absorption, in spontaneous emission, the momentum change is zero on the average. So if you consider the cycle, absorption plus emission, absorption followed by emission, which is called a fluorescent cycle, the limit momentum change, the velocity change is only due to the absorption process, and it is given by delta V equals V recoil equals h2 over mc. And this recoil velocity, when you put the number for optical photon, you find the recoil velocity on the order of 1 centimeter per second, 10 to the minus 2 meters per second, which is very small, and which explains why, for a long time, physicists have neglected recoil in light photometry. But if you put an atom in a resonant laser beam, after a cycle, the atom is again in the ground state in the laser beam. You can exhibit the second cycle, the third cycle, and many cycles, because it's always in light. And what is the number of cycles, W, that such an atom can form? And that nearly equal to this time, nearly equal to the computer does not recognize the police of the form. here it was, the mean number of cycles per second is typically determined by the lifetime, because each cycle lasts the time which is determined by the lifetime of the steady state, tau r. So within a factor of 2, the mean number of cycles per second is 1 over tau r. And since tau r is equal to 10 to minus 8 seconds, you expect that W is on the order of 10 to the 8 per second. That means that an atom in a laser beam, in a resonant laser beam, can undergo 100 million cycles per second. A lot of cycles per second. Now, what is the velocity change per second? In physics, the velocity change per unit time is what is called the acceleration. The acceleration characterizes the change of velocity per unit time, or deceleration. And what is the velocity change per second, acceleration A, is equal to velocity change W delta V per cycle times the mean number of cycles per second. That means to see here equal times 1 over tau r. Here equal is equal to 10 minus 2. 1 over tau r is equal to 10 to the 8. So you see that the acceleration or deceleration is given by 10 to the minus 2 times 10 to the 8, 10 to the 6 meter per second squared. Now, you know that the acceleration due to gravity, when the body falls in the Earth's field, the acceleration is 10 meters per second squared, g, what is called g. So you see that the acceleration of an atom in a laser beam is 100,000 times g. It's huge. You see that the cosmonaut in a rocket undergoing G2 or 3G is uncomfortable. Here it is 100,000 times bigger. That means that an atom in a resonant laser beam feels a huge force, which is called radiation pressure force. And of course, this force, which is huge, now you can use it for changing the motion of the atomic gas, what is called slow down and cool atoms. In fact, when you have an ensemble of atoms, the velocity distribution of this ensemble is characterized by a mean value and by a velocity spread around the mean value. Changing the mean value, reducing the mean value is slowing down atoms, but it's not cooling. In physics, temperature is not related to the mean velocity, it is related to the velocity spread around the mean value. The temperature characterizes the disordered motion of the atom. If you reduce delta V, the velocity spread will cool atom. And let me tell you first, before explaining how to do it, that by using radiation pressure forces and other type of forces which I have no time to explain, it's possible to slow down and to cool atoms by various physical mechanisms and to reach temperature on the order of 10 to the minus 6 Kelvin, the microkelvin. You know, in physics, the convenient unit of temperature is not Fahrenheit, is not Celsius, is Kelvin. And the lowest possible temperature is 0 degree Kelvin. Everything is completely cold. And room temperature here is 300 Kelvin. Okay? And the temperature we get by laser cooling is 10 minus 6 colder than room temperature. You see that? And velocity spread is on the order of 1 centimeter per second, but even less, a few millimeters per second. You know, at room temperature, you have 300 Kelvin, and the velocity of the molecule of nitrogen and oxygen around Earth in this room are on the order of 1 kilometer per second. So you see the start from velocity of atoms from 1 kilometer per second, and it goes down to a few millimeters per second. So you have a dramatic reduction of the agitation of atoms. Atoms become very quiet. So let me first explain more precisely how you can stop an atomic beam. You take an atomic beam coming from an oven with a velocity of the order of 1 kilometer per second, and you excite this atomic beam with a counter-propagating resonant laser beam. And the pressure of the radiation pressure exerted by the laser beam on the atomic beam decelerates the atomic beam. I'd like to give the following picture to understand that. Suppose that you walk in a very heavy storm of hail, small grain of hail hitting you. When you try to walk, all these grains are falling upon you and they slow down. Exactly the same thing. You have the atom moving, it shoots a lot of photons, absorbs the emitted, and then slows down. And it slows down with the velocity acceleration 10 to the 6. So if it starts with 10 to the 3 meters per second, it stops in 10 minus 3 seconds in a millisecond. It stops. And during this time, the decelerated motion is given, the distance traveled is given by a high school formula, A0 squared divided by 2a, which is 4.5 meters. That means that in a reasonable distance, which can be achieved in the laboratory, you can stop an atomic beam. Of course, you immediately should ask the following question. There is a problem with that method, because when the atoms start to decelerate, because of the Doppler effect, if they were in resonance with the laser light at the beginning, because of the Doppler effect, after a short time, there will be no longer in resonance because of the Doppler shift, and the force will decrease. So that's a big drawback, but that was solved by my colleague, William Phillips, who got the Nobel Prize the same year as me, in 1997. And he had a very clever idea of producing solenoid around the atomic beam with a number of terms which varies in space, so that you produce a gradient of magnetic field along this direction. The magnetic field is not uniform. And it turned out that in physics, the frequency of an atomic transition is changed by a magnetic field. It is what is called the Zeeman effect. And you calculate it depends on the magnitude of the field. It's proportional to the field. Energy shift is proportional to the magnitude field. So if the field varies, the shift of the atomic transition varies in space. And you compute the profile of the thing here, so that when the atoms move, the change of the atomic frequency due to the Zeeman effect exactly compensates the change of the apparent Doppler effect. And you maintain over the whole trajectory. And then you can stop the atom in a few 1 meter. That's a picture, a real picture. That you see here, that's the end of the solenoid. That stray light coming from the laser, and you see this trajectory represents the atomic beam, which is slowing down, stop, and coming back to the other. And you see the fluorescent light emitted by plutonium atoms. So you can stop the atomic space. And of course now with laser diodes, we can also change the method of the laser as a function of time to maintain the resonance condition. So let me now explain how it's possible to cool the matter. And first explain the simplest cooling scheme, which is called laser Doppler cooling because it uses the Doppler effect. And the idea is simple. Is the following one. Instead of taking a single laser beam, you take now 2 laser beams, counter-propagating, with the same intensity, the same frequency, new laser, but you detune new laser below the atomic frequency, nu A. New laser is slightly smaller than nu A. What happens? If the atom is at rest along this direction, there is no Doppler shift of the 2 lasers. So they have the same apparent frequency, they have the same intensity. These 2 forces are equal and opposite, they cancel out. And the total force is equal to 0. The atom is pushed in this direction, it pulls this direction with equal forces, and the net force is equal to 0. If the atom is moving to the right, with the velocity v, because of the Doppler effect, the counter-propagating beam will have its frequency shifted up, and the co-propagating beam will have its frequency shifted down. So this beam, nu L will increase, it will get closer to nu N. If it was smaller than nu L, it increases, it gets closer to nu N, it will be more resonant, more photons will be absorbed, and the force will increase. Contrarily, to this case, this frequency will decrease, it will get farther from resonance, less photons will be absorbed, and the force will decrease. So you see that as a result of the Doppler shift, the 2 forces will no longer be equal, and the force which will win is the opposite force. So the total force experienced by the atom will be opposite to the velocity, and for low visibility, linear in V. You will get what is called the discrete force. Exactly what happens, for example, in a pot of honey. If you have a spoon, and if you try to move the spoon, the faster you move the spoon, the bigger the resistance. This is what is called viscosity. So you have achieved a viscous medium, and this is why people call this device, this method, optical molasses. It's a pot of honey where you have replaced the honey by light. It is the light which produces the viscous medium. And for example, this picture shows you the real molasses of sodium atoms at the intersection of 6 laser beams, 2 along the X direction, 2 along the Y direction, 2 along the Z direction. So you prove the 3 components of the atomic velocity. And when you make the theory of this effect, you predict that the temperature which can be reached by this technique should be on the order of 200 microkelvin, which is already very good. But when people started to make precise experiments, precise measurements of the temperature, they found a different result. They found that the temperature was not 200 microkelvin, but 1 microkelvin, which was a good surprise. But usually when you do an experiment, it was less good than predicted by theory. Here it was a reverse. The experiment was better than theory. Before explaining why, let me try to tell you how it's possible to measure such temperature. It's not easy. You cannot put a thermometer in the optical wire because you have too few atoms there. Say too cold, the thermometer will be broken. So what you do is called the time of flight. You start with the molasses here, the 6 letter B, and at time t equals 0, you switch off the letter B. So atoms are no longer kept, they are moved freely, and they form a shower. And you detect them falling down by putting a probe laser beam at a few centimeters below, and when an atom starting from the molasses cross the beam, it gives a fluorescent signal which you detect by a photodiode. So you measure the distribution of time taken by the atom and crossing the laser beam. And this time of flight signal depends on the acceleration due to gravity, which you know. It depends on the spatial position, distribution of atoms, which you can determine by taking a photo of the molar. And it depends also on the velocity distribution, because each atom makes a parabola starting from its initial position and with its initial velocity and falling in the gravitational field. Now, you assume a certain weight for the velocity distribution, you calculate the expected time of flight signal, and you make a fit between the expected time of flight signal and what you observe experimentally. And by fitting the two curves, you determine the velocity spread that reduces the temperature. And in this way, you can measure the temperature quite accurately, and it is in this way that it was found that the temperature was about 100 times lower than expected. Now I have to explain why, and that was a nice result. It turned out that the explanation comes from optical pumping and light sheet, which were studied 30 years ago before. And the explanation is the following. We found it with my young colleague Claude, and the idea is the following. In the lower state of the sodium atom, you have many spin states, because you have angular momentum. Let me take the spin 1/2. There are 2 spin states, plus and minus. Now, when you have full laser beams, counterpropagating, since they are coherent, they interfere, and you have the standing wave with nodes and antinodes. So you have an intensity which is specially modulated, and also a polarization which is specially modulated. And I've shown you the ground state, since the laser is not resonant, it is detuned to the red, you have a shift of the laser. And the shift of the 2 spin states are not the same because the probability, condition probability starting from spin up to spin down to the excited state are not the same. So you have spatial modulation of the spin up, spatial modulation of spin down, which are not the same. And since the light is not detuned too far from resonance, you have also optical pumping wave. The atom can absorb a photon from the spin state and re-emit a photon and end in another spin state, which is what is called optical pumping. And we can achieve a situation like that, where an atom starting from the spin, right, this is the modulation of the spin down, this is the spatial modulation of the spin up. An atom starting from the spin down, say, in the bottom of the valley, can climb this potential A and reach the top of the hill where it has a certain probability to be optically formed in the other state, that it will to the bottom of the valley, from there it climbs again, up optical forming on the side, and so on. And you see that the poor atom is always climbing potential hill, exactly as the hero of the Greek mythology, Sisyphus, who was condemned by the gods to roll up the rock at the top of the mountain, and when he finished the work, he went at the top, the gods were putting him at the back, and he was to jump again and again and again. And this is what we call this ski, the Sisyphus schooling, the poor atom climbing all the time. And you can make the theory of this, make experiment, precise experiment, and you can prove that this is what happens. That allows you to reach the microkelvin rank. And in fact, in our laboratory, we were able also to find and to discover other cooling techniques, even more efficient than this one, allowing you to reach the nanokelvin rank, 10 to minus 9 Kelvin, but I have no time to explain it. I would like just to introduce another idea of laser trap. I explained to you how to be able to control the polarization, the velocity of the atom. Let me now try to explain how to be able to control the position, how to be able to trap atoms. Here again, it's an application of light shield. What introduced now laser trap. If you take a laser beam, and if you focus it tightly, you see that the intensity will be maximum in the focus. Because the highest concentration of energy. If the laser beam is tuned to the red, as I explained to you, the quantity will be shifted by an amount which is negative and proportional to the light intensity. So if you cross the laser beam in any direction, this one on the top, the ground state will be going down, passing through a minimum and going up, and everywhere. So the energy of the ground state as a function of space exhibits the minimum, which is a potential wave. And in this potential wave, you can trap atoms if they are close enough. This is what is called a laser trap. And in fact, this scheme allows you also to trap any kind of biological, not only atoms, but also biological objects like a virus or bacteria. By focusing the laser beam, you can catch virus or bacteria and move it by moving the laser beam. This is what is called now optical tweezer. It's a very important tool in biology. And there are other crafts which I have no time to explain. Finally, I would like to give a last example of manipulation, which does not use light, but which is very beautiful, and which complements laser moving. Once you have reached very low temperature by laser moving, you can continue by what is called evaporation. And the idea is even simpler. You take atoms which are trapped in a potential wave with the depth U0, and if the density is high enough, the atom collides. And you have elastic collision. And in elastic collision between two atoms with energy E1 and E2, they change energy, they give E3 and E4, of course, with conservation of the energy, which means that E1 plus E2 is equal to E3 plus E4. If E4 is larger than the potential depth, the atom with E4 will escape from the wave. It will leave the wave. The remaining atom will have an energy E3 much lower. And by colliding with the other one, the sample will thermalize to a lower temperature. This is exactly what you do when you blow air above your cup of coffee or tea. You evacuate the hot molecule, and the remaining molecules are frozen. This is what is called evaporation. By this technique, it's possible to move from the microkelvin achieved by laser moving to a few nanokelvin. You can go much faster. So you see now we have at our disposal a lot of methods for controlling everything about atoms. Position, spin, velocity. Now, I would like now to discuss, before discussing the application, just to give you an idea that an example of a bulb a vessel of about half a liter filled with cesium vapor. And it is at room temperature, so you can take the vessel with your hand, and you apply laser beam, the magnetic field gradient, and so on. And in the middle of the cell here, of the vessel, you have the orange spot, which is the source of light emitted by about 100 million cesium atoms, which are trapped in the middle of the cell at a temperature of 1 microkelvin. But the sample of all atoms contained in the center of the cell, which is at room temperature. So you have the sample of atoms upon which you can now do physics, you can do some new experiments. And the next slide shows you an idea of what the complexity of the experimental center. Then you have a table about here, 2 meters by 3 meters. Then the Zeeman flower flowing down the beam. The beam is coming from here. It is trapped here, and all these components are just optical lenses for using diode for producing the laser beam, for polarizing them, for dealing. It looks complicated, but it's not so complicated. It's not terribly expensive. Absolutely expensive, but it's an experiment which can be managed by 2 or 3 people, compared to the high energy experiment, which requires much more money for people. So now, in the last part of my talk, I would like to address the question, what can we do with this color? And I would like to give you the first general idea. Cold atoms have slow velocity, so they move slowly. So you can observe them for longer time. Like the thermal atom, which moves at kilometers per second. And in physics, there is a time-energy uncertainty relation which tells you that the longer you observe the system, the more precise, the better you can measure atomic frequency. So with cold atom, you can measure atomic transition frequencies with a much higher accuracy. And you can use this frequency for making better clocks, better atomic clocks. Second application, you remember that the Broglie wavelength is given by lambda de Broglie, we call H over mv. V is in the denominator. If V is small, the lambda de Broglie is large, which means that the cold atoms have a very long, large de Broglie wavelength, and that means that it's easier to observe with a cold atoms the wave aspect of matter. And a whole series of new experiments are being performed which look like interference experiment done with light wave, except that you replace light wave by the one wave. And that is what is called now atomic interferometry. And third example, that when atoms are not only cold, but dense, still gas, but gas, you can reach a situation where the mean distance between two atoms is on the order or smaller than the Broglie wavelength. That means that the wave function of the various atoms overlap, they start to interfere, and the phenomenon which was predicted by Albert Einstein following the statistics of Bose in 1924, so-called Bose-Einstein condensation occurs, which means that at this temperature, the macroscopic, all atoms will condense, will go in the same quantum state, the ground state of the trap which contains them. So we'll have a macroscopic number of atoms, a million atoms, all with the same wave function. This is what is called the macroscopic matter wave, the Bose-Einstein condensate, and that new state of matter is presently the object of thousands of investigations in the world, because they are really fascinating. So let me first explain to you the clock. You know, the clock is a quartz. It's an oscillator. Every of you have a quartz in your watch. But if you take two different quartz, they are not the same frequency. And if you take a single quartz, as a function of time, the frequency will change. It varies. So if you want a very precise clock, you have to lock the frequency of the quartz to a fixed value to prevent it from moving. And if you lock it to the frequency of an atomic transition, which is universal, the frequency of cesium atom is the same very well, then you have what is called an atomic clock. So the principle of atomic clock is the following. You start with the quartz oscillator, you generate an electromagnetic wave which interrogates describes the transition between two atomic energy levels, E1 and E2, separated by splitting E2 minus E1 H naught. So the transition frequency is mu naught. Okay, and in fact, internationally, the second, the unit of time, is defined through the transition of the cesium atom. So the cesium atom is taken as a unit of time. Transition between two states of the cesium atom, to well-defined state, serve to define the second internationally. And then, so you drive the measurement, and then with the loop, the servo loop, you correct the quark frequency to remain on the center of the transition, atomic transition. This is an atomic clock. In fact, what you do, by scanning the frequency of the quark, you find a resonance, atomic resonance, centered at mu naught, with a certain width, delta mu. All atomic transitions have a width. And what I told you just before is that the longer you observe the system, the smaller the width. Delta mu can be shown to be inversely proportional to the observation time. So by taking cold atoms, you get very narrow line, and the servo can be more efficient, more precise. So this explains to you why atomic cold atoms are useful for clock. And the clock is done in the following way. You take a ball of cold atoms, and this effect, you throw them upward. And you make what is called a fountain of atoms. You have a molar here of cesium atoms, and with the laser pulse, you throw them upward. And they go, they cross the loop where you measure the radio frequency transition, the microwave transition between the two states. And you see they go once on the way up and once on the way down. It's exactly like the fountain of water, except that most water drops are replaced by atoms. In a usual clock, up to now, you have a thermal cesium beam, 1 kilometer per second, very fast. Crossing, you cannot make a clock larger than 1 meter. So 1 kilometer per second, crossing 1 meter, you get 1 millisecond observation time. Here, the time is like that, 0.1 seconds. So you get 2 orders of magnitude, and you get much narrower line, and the clock will be performed presently in Paris by my colleague Christophe Salomon and their colleague, is the most precise clock in the world. It has the stability of 1.6 10 to the minus 16 for an international value, and an accuracy of 7 10 to the minus 16. To give you an idea, if you start such a clock and stick with 0, with this accuracy, stability, 300 million years after, it will be off by less than 1 second. So you have a very precise clock. And that's about 1,000 times more precise than the all existing clock. And you know that with such clock, you can, of course, improve dramatically the efficiency of the GPS system, global positioning system, which use atomic clocks in satellites for determining the position of radioids on Earth. You can synchronize the high flux of the information in the optical fiber with a more precise accuracy, and you can of course make more precise tests of signal volatility and the gravitation theory of Einstein. And of course, you cannot make fountains higher and higher. It's not realistic. And the next idea to improve the clock is to get rid of gravity. Because, you know, the time is limited by the gravity. And so we started in France a series of experiments done in what is called the zero-G flight of the CNES, Centre National d'Études Spatiales. You take an Airbus or a Caravelle, ascending machine like that. The pilot steps the engine, so the flight is free. It makes a free fall, like that. It falls, and when it falls like that, the pilot puts the engine back again, and makes a second parabola, and so on. And each parabola lasts about 20 seconds, and the flight lasts 2 hours. And you have in the plane 20 different groups doing microgravity experiments. And if you are sick for 2 hours, only young people are admitted because I was not too old to do this experiment, but the experiment has been done in several campaigns. That the picture of the cold atom groups here, floating during the parabola, that's the equipment, and it turned out that it's possible to stabilize the lesion to make the experiment in this condition, and we got the possibility now, the agreement to put such a fountain, such equipment in the space station. And this project is called ACS, Atomic Clock Assembly Space, that's the International Space Station. If the program is not cut by budget consideration, it will fly at 207, and we'll have a cold atom clock in this station, delivering time, synchronizing all clocks in Earth, synchronizing them, and allowing one to make a very precise test of general output. So that's a big problem. Second application, the long double wavelength. And an experiment is very beautiful, which I like very much, has been done in Japan by a colleague, Shimizu Takuma. And what these people did, they repeated the young experiment with aston instead of photon. They started with the monad of the metastable neon atom, Claude, and they switch on the beam, the laser beam, so they don't fall. They fall through a screen with two slits, and they have here an observation screen. Exactly the same experiment I described at the beginning of my talk. But you know, here, since the atoms are cooled, not in the ground state, but in a metastable state, which has very long lifetime, a few minutes, so it's like a ground state. But since they have an internal energy which is high, when they hit the plate, they give rise to a lot of electrons, and you can detect the atom one by one. I saw the experiment in Tokyo. I saw also the movie, and when you see on the screen, you see point. At the beginning, it looks completely random. Each atom is right like that. And when you have enough data, you what you observe. You observe each point here is an impact of the given neon atom. Each atom is a localized impact. But clearly, the spatial repartition of impact is spatially modulated. You have more impact here, than here. You have bright fringes and dark fringes. You get exactly something similar to what you observe in the low fringes. Okay? And when you apply the well-known interference formula that you have learned in high school, you find exactly the good result provided you replace the light wavelength by the double wavelength. But this experiment is very difficult, in my opinion, because it clearly exhibits the wave particle duality for atoms. Each atom is a particle, because each atom is right to localize impact. But at the same time, each atom is a wave, because if you don't take the wave aspect in account, you cannot understand the fringes. And the connection between the wave and the particle is of probabilistic nature. Using the wave, you can calculate the probability to find the particle in a given form. Because the square of the wave gives you the probability to find the particle in a given form. It's a math-born interpretation of quantum mechanics. And now this experiment is used in all quantum mechanics courses to explain to students the feature, the mysteries of quantum mechanics. Okay? And of course, that's a very simple experiment. That was not a proposal experiment using interference between the wave. For example, if you take two de Broglie waves, one coming in this direction, one in this direction, they interfere, and if you rotate the platform where the experiment is located, the frame moves, that is called the Sagnac effect. You make a gyrometer which allows you to measure the rotation speed. Presently, the plane uses the laser gyrometer using laser light for navigation. Okay? But it turns out that the gyrometer using the Broglie wire are expected to be much more sensitive than laser gyrometers. Of course, technology of the Broglie wave is not yet as developed as laser wave, so laser gyro has still a future. But perhaps within a few years they will replace by gyro. Let me just tell you that presently the de Broglie gyro allowed to measure, is sensitive enough to measure the rotation speed 10,000 times slower than the rotation of Earth. The Earth makes the turn in 24 hours, which is very slow rotation speed, but you can detect rotation speed which are 10,000 times slower. That gives you an idea of the sensitivity of the interferometer. You can also detect gravity gradient very accurately with different interval rate, and you can, for example, look for all the Earth, because you can detect variation of the gravitational field. So you have a lot of applications. And finally, I say a few words about Bose-Einstein rotation that Einstein and Bose have presented here. What happened is that in 1923, the physicist Bose tried to recover the Planck's law by applying radiation field as a set, a gas of photons, and by introducing a new way of counting the number of microscopic states of the photons, but counting them in a different way to calculate the number of microscopic states describing a macroscopic state. And he found a new statistic leading to the Planck's well-known Planck's formula. Einstein received this paper because Bose was not able to publish it alone. Einstein found it very interesting. He helped Bose to publish it. He published only Bose, but only paper with Einstein did not sign the paper. Just helped him to publish the paper. And he found it very interesting. And 1 year later, he extended the idea to a gas of particles, not a gas of photons, but a gas of particles. And when the particles are in the mass, not like photons, photons have zero mass. Einstein found that at a low temperature, all atoms in the track should condense in the ground state of the track, of the box will contain the atoms. And that happens when the mean distance between two atoms is smaller or on the order of the double wavelength. And that's extremely interesting because then you have a macroscopic number of atoms in the same wavelength. You know, when Einstein published his paper in 1924, temperature he calculated for this condition was like Cohen-Tannoudji, and everybody considered that as a purely academic work because Einstein was calculating the process of a perfect gas without interaction. But at this temperature, the equilibrium state of one substance is liquid or solid. And in a liquid and solid, it cannot neglect interaction of both on the system. But with the laser cooling, we can reach this temperature, and since we need 3 body collisions for forming the liquid and solid, we can maintain this Bose condensation for a long time before the system ends finally in the liquid or solid state. So it was possible in 1995 to observe for the first time BEC in a gas, Bose-Einstein condensation in a gas, laser cooled and evaporatively cooled. And the 3 people who do this work, Eric Cordet, Carl Weinman, and Prof. got the Nobel Prize in 2001. So that was the second prize given after the Nobel Prize in 1997, 2001, for application of this transformation. So let me tell you a few words. That's the pictorial representation of what happened of the atoms where the liquid, the temperature, for a value high compared to the critical temperature predicted by Einstein, to Tc and below Tc. When you are high above Tc, the double wavelength is very small, so you cannot see the wave aspect of atoms that behave as they are all. So the classical description is very. When you decrease the temperature, you start to see the wave, but the wave packets are still far apart. So you can still neglect the wave aspect. But when you reach Tc, then the waves start to mix and overlap and interfere, and then the population of the ground state becomes populated. And when you are well below Tc, all atoms are in the lower state. And you can ask, how can we detect this effect? And the beauty of cold atoms is that you can detect them by looking at the modification of the spatial distribution of atoms. You expect that the spatial distribution of atoms should have a double peak structure. You have the narrow peak here, which corresponds to the atoms which are condensed in the ground state of the trap. And in the ground state of the harmonic trap, the width of the wave function is very narrow. So you expect a narrow peak corresponding to the atoms which are all in this narrow wave function. And superpose, you have a pedestal here, right over, which corresponds to the atoms which are not yet condensed, which are in highly excited state of the trap with broader wave function and with a broader spatial distribution. So you see a double peak structure. And how can you detect it? You start with a cloud of atoms in the cell here, you make a parallel laser beam, resonant, and you measure the shadow introduced by the laser beam crossing this cloud of resonant atoms. And you measure the total absorption length of each part. So by projecting the image of this plane on a CCD camera with a lens, and you measure the 2D profile, optical thickness of the cloud, this technique. And by using the false color picture, this is the first picture which was obtained in 1995 by the Boser group on Comedium. You see above the critical temperature, you have only the thermal cloud, atoms are not condensed, the growth is that. When you reach the critical temperature, you see the narrow peak appearing, and when you are way below the critical temperature, you see only the condensate. Then you have a pure condensate, a million atoms, all in the ground state of the harmonic potential wave containing the gas. The same picture here for sodium, obtained at MIT, still better signal-to-noise ratio, and since that time, EEC has been observed in a lot of other substances. Now it becomes a universal feature. And what I would like to try to explain to you why this is important, why people are so excited. It's because this macroscopic object, the condensate, exhibits these macroscopic matter waves that you can see by eye. The condensate has a dimension of a few hundred microns. You can see by eye. So these macroscopic objects have quantum properties, superfluidity, coherence, so which makes them very similar to other systems which up to now were only found in dense systems like superfluid helium or superconductor. The new feature now is that we have these properties appearing from very dilated systems, about 100,000 times more dilated than air. Whereas superfluid helium is 100,000 times more concentrated than air. And in these dilated systems, atom-atom interactions are much weaker, and they can be described much more precisely. So we have in conditions much closer from Einstein theory. And we can include the effect of interaction in a much cleaner way, so we can understand the effect of interaction much more deeply. And first of all, it has been discovered recently that by changing the magnetic field, and you can change the collisional properties of two atoms, and you can change their interaction. You can progressively change the gas from the attractive feature to a repulsive feature and to a zero interaction. So you have a node now to control the interaction. And it explains now why there are about 1,000 papers appearing every year on EEC, both theoretical and experimental. It's a very excellent field. So with my next slide, I would like just to make a list of applications which come out from both these fields as described today. It's possible to make magnetometers and lasers with optically formed atoms. I described to you how it's possible to make MRI of the line with polarized helium-3. It's possible to make ultra-cold patterns using for atomic clocks with stability and accuracy and magnetic 16. It's possible to make what is called atomic photography by taking coherent atomic beams and focusing them very tightly. You can deposit atoms on the substrate with the spatial resolution of a few 10 nanometers. You can make nano-lithography. You can make atomic radiometers, atomic gyrometers, atomic interferometers with the waves. You can make what is called atom laser. And that can be understood in the following way. When you have a laser is a cavity, two mirrors. Inside the cavity you have modes of the cavity. And one of these modes, one of these quantum states of the cavity contains a macroscopic number of photons. And one of the mirrors is slightly leaking, and you have a beam of current photons coming out. And that's the laser beam. Now we can take a condensate. In a given state of the cavity of the trap, you have a macroscopic number of atoms, all in the same state. And if you make a small hole in the trap, you have a beam of coherent Debray waves coming out, and this is what is called atom laser. One of the atom lasers is here. That's a condensate, and that's a beam of coherent atoms coming out. So you can make the equivalent of the laser beam, except that you replace the light wave by Debray wave. Also, a lot of work is being done now because we can manipulate atoms in a much cleaner way. We can use atoms as bits of information. You know, in computers, in classical information theory, but I would like to emphasize that all these developments were not planned. All the results from the breakthrough discontinuity change in technology, which is always the case, because new ideas come and produce a dramatic change. I'm sure that you have all been to how all vinyl records, 33 turns per second or even 45 turns per second, and even some of you have 78 vinyl per second, all records. And it has completely become obsolete when you see the CD with laser reading has been found. And probably now the MP3 are replacing the CD reader, and perhaps in this area we have a new technology. So you see that it is very dangerous to try to develop a given technology as far as possible and to neglect basic research. Because basic research will introduce new ideas which make the given completely obsolete. And I'm sure that the technology which will be used in 20 years from now is what is being studied in the basic research laboratories today. So it is why it's important to maintain a very strong basic research. So it's time for me now to conclude, and this will be my last slide. I think I want to have convinced you that our ability to control, to manipulate quantum systems like electrons, ions, atoms, molecules are dramatically increased during the last 2 decades. Now it's possible to manipulate to observe a single electron, a single atom, a single ion, a single molecule. That, of course, allows opening completely new research fields, allowing us to ask completely new questions and new interrogations. And essentially, when you ask new questions, it's exciting because then you can discover new things. And we can hope reasonably that this will lead us to a better understanding of the world around us and to interesting things. And I think, to conclude, I would like to say that the basic research is, in my opinion, very important for at least 3 different reasons. First, for culture. It improves our vision of the world. Every new discovery changes our vision of the world. The relativity theory has changed our conception of space and time. The genetic code has changed our conception of life. The astrophysical investigation have shown us that stars have a birth, the life, and the death, and the universe is expanding, so we have a completely different view of the universe. So that's a cultural improvement. Also, second point, solving the various problems, energy, environment, health that mankind has to face. We have to find new source of energy, we have to improve our health, we have to protect our environment, and I'm convinced that this will be achieved by doing more science, not less science. Unfortunately, there is bad picture which is often associated with science. People say that science is for ignorance, for the bad science, but that is, I think, a mistake. If we do good science, I think we have to do good science to solve this problem. We cannot escape. We have to find new source of energy if we that every country lives in a decent way. And third, I think also it's important to keep in mind that we not develop scientific education. Because the scientists, science education teaches the young kids that the sense of observation, the sense of modesty, because the real researcher knows that what he has to learn is much more important than what he knows. And the scientist is asking new questions. He has an open mind, a critical mind. He cannot be misleading. He knows that everything has to be questioned to progress. And there is a sense of dialogue between people. So scientists, international, in a given laboratory, there are people coming from all over the world discussing it. And when one people make a mistake, they recognize the mistake and because it's condemned by the government and the other. So science is and culture a way of promoting dialogue. And I think in the beginning of this century, where we have a lot of fundamentalism, extremism, racism, I think it's important to maintain, to improve our education system to have best protection against these bad things. And I think also that we will promote peace, which is the most important. Thank you very much.
Thank you, Professor, for your very interesting talk. I would now like to open the session for any question. Please raise your hand if you have any questions. Yes, sir.
First of all, I'd like to thank you for a truly inspirational lecture. It's been a long time since I've been in a physics lecture myself. I'm now beginning to wish I perhaps study physics at university. I'm a mechanical engineer by trade, and traditionally mechanical engineers look at things on a macroscopic scale. More recently, mechanical engineers have been interested in nanotechnology, and the limit they face there is manipulation of atoms in order to build useful devices. Do you think it's possible that we may see some further development of your work such that we can manipulate atoms on a higher temperature level? On a higher temperature level.
You know, I think what you are referring to is the very important field too, which is different from this one, which is nanotechnology, where people use tips near a surface and use atomic force microscopes to manipulate atoms in the surface. And that gives works at much higher temperature than this one. And it can allow you to move atoms with a piece of metal, for example. You have also what you call the tunnel microscopy, performed by Prof in Switzerland, because of very fast on that. That's another example of manipulation. You know, here it's manipulation of atoms in the gaseous phase, when atoms are very weak. And then the intent of this pattern. But of course, there are also closer investigations where you can manipulate atoms and nanotechnology is a very good example. And people are doing fluorescence or nanotubes of carbon, and there are a lot of ways of protect. So that's another field. It has time for other fields.
Yes, sir.
You mentioned that the achieve temperatures of the
You
mentioned that you could achieve temperatures of the order 10 to the minus 6 Kelvin using the laser methods, and that from those temperatures on you could achieve lower temperatures by using evaporation, escape from the quantum wells and so forth. At what temperature does the evaporative effect become viable? In other words, can you start that process from 1 Kelvin or more? Presumably it cannot be used from room temperature evaporation alone to achieve very low temperatures.
I think what the question you're asking, what is the lower limit you can go to?
No, when can you start evaporative cooling?
Oh,
You cannot start from room temperature and achieve
because you must have already a sample which is very cool, cold, start having collision rate high enough. To have the evaporation starting, do not have a collision rate which is high enough. In fact, the number of elastic collisions, the time between two elastic collisions experienced by a given atom must be short compared to the time between inelastic collision with taken atom out of the fire. Because you know, when you have a sample of Paul atoms, you have always residual gas in the vessel. And collision between the Paul atom and the residual atoms of the air, because you cannot make a perfect vacuum in the sample, take the atom out of the fire. Okay? And to evaporate, you must have enough rate of elastic collision compared to the inelastic rate. And to do that, you have to reach sensitivity high enough. And this is why evaporation starts only after evaporation.
So you need temperatures of 10 to the -3, 10 to the -4. What sort of temperatures
So the evaporation starts, you need a few microkelvin to start evaporation.
Any more questions? Yes, sir.
Why you is there that you are into? Why you is there that you are into?
Sorry, I didn't catch your question.
Why you is there that you are into?
Why do you take this field of research?
What makes you interested in this type of research? You know, I think in research, one important motivation of research is curiosity. Curiosity and fun also. I think there is some sort of fun when you do research, when you try to find the tricky way of doing something which nobody else has imagined. You are always happy and excited. It's a combination of curiosity, desire to understand what happens. I think the main drive for research is not application, not finding application. It's curiosity. You try
Curiosity and you want to know.
to know. And
It's like you are going
and also, when you have a nice trip happening, you are happy.
Very happy.
Yes, that's yes, of course. That's also the main. I would like also to say that a very important fact in my personal life is how the luck that you have in my childhood. My parents taking care of my studies very carefully. Excellent high school teachers who communicated to the patient for mathematics studies. And when you come I found the physicists outstanding people were attracted there. Was not only the physical understanding, but explaining what he was doing. Very clear, but he has also a relationship, very human relationship, that was very respectable that. So it was a personality, attractive personality, which drives you. So it's important to find a good mentor for
Yes, sir.
I wanted to focus more on the end of your talk. I'm a math teacher also. I try to do what you're talking about. I found I've noticed that many great scientists are not just good scientists, but they're also great humanitarians. Einstein and Einstein. And I just wanted, it's such an important part of your talk. I was wondering if you could just give a few more words about education and helping people become connection between science and becoming a person and developing yourself as a person.
I think I come back to curiosity and when you are a scientist, you really try to understand, and it's absolutely basic when you go to talk to people, to discuss with people. Because when you have an idea, it's initially vague, and you try to convince other people that what you are thinking about is good or not, and you have to share ideas. And try in this way to respect each other. You know, the real scientist cannot think that he detains the absolute truth. You know, any scientific theory explains at a given time what is observed, but generally it's a model. And when the observation becomes more precise, you have to change the model and to take a new model, including the previous one, and going further. For example, to cure Newton and gravitation. Excellent. There are a lot of things. And then we found gravitation of Einstein. Okay. And people are trying very hard to find insufficiency of the gravitation theory of Einstein in our physics and to go further. So you know, the scientists know that we have no absolute truth to impose to somebody else. We have to respect and we have to try to find the progress. You know, there is no end to it. Every new discovery has opened as many new questions, even more new questions than those questions have been solved. So I think this progress was a better understanding to a better dialogue so that I find useful for me. And this is why I think that is important part of the human culture.
Any more questions? Yes, sir.
I wondered if your research has given you any insight into the contradiction between insight into the contradiction between quantum mechanics and relativity, difficulty, all present in your work.
You know, we are things are working at very low temperature, the velocity are very weak, and relativity correction are extremely small. But you know, there are two. That I know experiments which have been done by Gabriel on the single electron. It's cool at very low temperature, but the precision of the experiment, the accuracy, is high enough to detect relativity correction. And of course, the clock, you know, the ultra-precise clock, which was two clocks at different latitudes, because the habit shift predicted by the time they should not oscillate at the same frequency. And for example, now in the GPS system, to calculate where you have to take into account the fact that the clock behind the satellite are not the same time as the clock you have in your car or in your you are to improve the general relativity concept. And also, I didn't have time, but the very exciting experiment, which is done with atomic clock, is to take two different clocks, one with rubidium, one with cesium, and to compare the two oscillation frequencies as a function of time, going 3, 4, 5 years. Okay? Now, there are certain cosmological models which predict that the fundamental constant of physics, A, C, should vary in time. So if this is the case, the ratio of the two frequencies should also vary in time. And by looking at this ratio, we can test this model. And that's an example of how doing a laboratory experiment we can address different questions about the cosmology of our universe.
Yes, sir.
Just a very interesting question that has plagued my mind for some time. We have developed photography where we are able to take photographs of speeding bullets and move very quickly. Can we photograph light, the edge of light, turn on a light beam? This light beam is going through space. Can we photograph what
hard to decipher the what is it?
You know, I noticed that as a kid, that it's kind of what is called an antecedent or antecedent-like process. And I was recently in Germany, in Garching, and I found an experiment where people using the antecedent kind of light, light lasting less than 10⁻15 seconds. For example, through video, and by technique of nonlinearity, they were able to make a picture of the possibility of the light bulb. So with a short bulb, the light will execute only 2 or 3 oscillations, because the duration of the bulb is only 2 or 3 times the error, and we are able to control this and to make a picture of it. So some sort of answer to your question. That can be achieved now.
Yes.
Can you give us some words of inspiration and guidance to reach the heights that you are at present? Some words of inspiration.
Yes, I think I would invite you to study mathematics because of course chemistry, because in biology, I think science is exciting because when you try to do good science, you spend a lot of time, a lot of pleasure. When you understand something, it's the greatest pleasure. I think that science is a good experiment, a good theory, provides you some artistic feelings like a good piece of music or good painting. I think there is a beauty in the equation, there is beauty in the physical phenomena which can drive you to do more science, to try to learn more. And the important point is to try to discover that future of science. It's not science, it's not a boring exercise of calculation. You should find in science in the physical phenomena, in the biological phenomena, in the chemical actions of the
Yes, sir.
So I'm wondering that as a last application of use has been able to instead of using the air or use the wires. The thing that we have to avoid nowadays is the regular wires. That this idea can be applied into the media instead of use the basic mediums as the medium on the guidance, the voice level, the lips, can be used by reducing the temperatures and use the atom as the medium to transmit and also as the energy to avoid the radio interference and the particles.
Already, it seems to be, as I mentioned, the laser technology with fibers with very low absorption, and with solid state laser like this one is so advanced that I think it will take a long time before atom lasers become as efficient. Just a question of technology. When the laser appeared in the 1960s, these systems, they became so bad, and a few people were considering that they would be useful. So, no one with the technology of atom becomes more and more difficult to reach the same state. I can say that already now there are people trying to make home atom experiments, not as large as the one I showed you by the meter table, but to make on the microchips the miniaturized component to make a little condensate on the microchip. And a lot of people are trying to do that, to miniaturize the body segment. And if it becomes but for the communication system, the fibers avoid a lot of problems of the can guide the fiber a lot of information. And the quantum cryptography I mentioned use very distribution in the fiber, and people have been able to put the fiber below the leg in cinema and to communicate between two people at 20 kilometers apart, and to exchange messages by this quantum frequency. So some are moving rapidly, but we don't know yet what is the most important breakthrough. Yeah, sure. But then you need to know what that is. Then you need very precise clock. Every computer, every communication system has a clock to determine if you have a very precise clock, then you can make a very precise timing of the flux of information.
So next will be the last question.
I don't know the answer. Nobody can predict. We know at a given time that there are certain things in physics. You know, I would say two things. First, great pleasure for me, for my family, for my colleagues, because it's a great achievement. Because I feel that what you have done is well appreciated and with a good appointment for one person. At the same time, a lot of burden which falls upon you. You have a lot of data to write, a lot of conference to do, a lot of education, and life becomes very difficult sometimes. So, but of course, we can complain. Life changes quite a lot. And we have to be careful to keep certain time for continuing the research, trying to find time for yourself, for your family, for your
I would like to call on the great one to pass on board of thanks and make a presentation to Professor Cohen.
Mr. Tannoudji, I think you have made something very difficult, very easy, so that it will be an inspiration for the younger generation to follow certain footsteps that you and many good scientists have taken. And I wish our Prime Minister would be here today so that we would uplift the study of science in Thailand. And it has been not a very good phenomenon over the last 50 years that we have not paid enough attention in the study of science in our country. And because we have not promoted enough good teachers. And if you have good teachers in science and maths, I'm sure we would have many, many more young scientists and young mathematicians that would discover more of this fundamental knowledge. And I guess today I must apologize for my jumping the queue. I was so excited to listen to your lecture instead of inviting Mr. Ue to give a little short talk about how the Peace Foundation and Bridges was able to bring all the Nobel laureates to Thailand since last year and this year and for the near future. And we are very lucky to be part of this program, that we are able to invite you to come to this university. And I'm sure that our friend there will give you a little news about what's going to be followed in the next few months, because many Nobel laureates have been invited to Thailand. So on this occasion, on behalf of all our listeners, I'd like to thank you very much, and by show our appreciation to Professor.
Ladies and gentlemen, thank you very much for your attendance. And please note that the next talk in this series by Dr. Lawrence will be held on January 14th, 2005. The professor Kilkenny will deliver an address titled The Development of X-ray Astronomy. We hope that you will all be able to attend. Thank you.